like I said, whoops, I'll be going over this document. By the way, does everyone, yes?
I was wondering how to study for it, because their slides are a little redundant and a little useless.
Okay. Well, if you're just looking, if you have good, comprehension, then the textbook is pretty nice. But it's also loaded with useless things. And the lectures aren't recorded. Damn. I don't know, actually. I think you should just scroll through the slides and make notes, and then I'd probably just work off of the notes. I've also posted a lot of notes. So anytime you want to check your understanding or something, I've put my perspective on a bunch of things. So maybe that helps. So check those out.
I do that, but I'm just wondering.
Anything else?
Provided course material.
No? Okay. So we're going to start. So question number 1 is just true and falses with justification. And the way this is going to work is I'm going to give you a quick 30 seconds, and then I'll sort of take a poll, and then if someone's brave enough to answer, I'll take an answer, and then we'll try and justify it. All right? Yes?
We don't have any true and falses tomorrow on Friday, right?
Do I have what? Sorry?
We don't have any true and falses on Friday, right?
No true and falses. But I think this is a good thing for developing your core understanding of certain concepts. Okay. This is visible to the people in the back too, right? Okay.
I think you should turn off the light.
Turn off the lights? Haven't heard that in, oh, no, I'm just kidding. There we go. Is the camera still fine with these lights off? Nice. Okay, that should be enough time for part A. So I'm going to take a poll. Raise your hand if you think it's true. 1, 2. Why is everyone looking around? Your answer should come from within. Okay. Raise your hand if you think it's false. More people. Why? For someone who thinks it's false, why?
Because it detects negative cycle and flow, not the positive capacity.
Well, the capacities are always positive, real capacities, so there can't be negative flow on anything. Yes? Yeah. So I'm not sure how explicitly this was mentioned, but we have integer capacities implies termination. There exist flows or flow networks where the capacities are non-integral, and because of that, the flow, at least Ford-Fulkerson, never terminates. In fact, there are some cases where the convergence of Ford-Fulkerson is not equal to the actual max flow as well, right? And this happens when you have irrational capacities. Right? So if you have irrational capacities, there is a possibility that Ford-Fulkerson always ends up picking like a weird path, and then it never terminates, and it converges to the wrong value. One quick note I want to say. So if we have integer capacities implies termination, Do we have rational capacities implies termination? Let me repeat myself. If the capacities are rational, so they can be written as P over Q, where P and Q are positive integers, can you guarantee termination? Yes. Why? Yeah. You scale up. You take the lowest common multiple of all the denominators of all the capacities, and you just multiply every capacity by that lowest common multiple, and now you just have a scaled up value of the flow network, and then you can compute your max flow with those integral values, and then scale down. Does that make sense? Nice. Okay, that's all I have for part A. Yes?
Do they add values to, like add to any positive or negative values to pitches and still scale it down at the end? Is that a property of
No,
flow as well?
because adding capacity or removing capacity will change the flow network. Scaling does not change the flow network. It's just the max flow just gets scaled, right? I think we'll get to see an example of this. Okay, part B. I'll give you guys another minute. Let me not forget to give out candy. This one's for you. Not in a room this tiny. I don't want to hit someone. I don't want to get sued. There you go. Yes, I learned it from the best. Okay. Time to take the poll. Raise your hand if you think this is true. Okay, a couple people. Why do you think it's true?
Like one algorithm that comes into mind is dividing it, and when you get to the base case, you take only one of the elements,
Mm-hmm.
and then that would be and log in, given that we would have to merge it back.
Okay, potentially. I'd need to do the analysis to figure out if it's n log n. Raise your hand if you think it's false. And why do you think it's false?
Because this is kind of similar to the what's that function? The one where you find. Never mind. Sorry.
I think you're on the right track.
It's very similar to that. The top five.
Mm-hmm. Mm-hmm. Yeah, order statistics.
Order statistics.
Okay, guys, if you ever see anything that says the median, order statistics, first bet, all right, best bet. If I want to, how long will it take me to find the median?
Well, you need to divide it by 2.
Well, we've done order statistics. I just need the runtime.
Log n.
No, it's not sorted.
I'm not sure.
Yes. O of n, linear time. Okay, I have the median. What do I do next? How can I create a new array? I now know the middle value, and I have all the values. What can I do? Yes?
Take the first one over 2, put it on the left or right.
Yeah. So what you can do afterwards is you can sort of, it's not fully sorted, but it's sorted with respect to the median. You can use the median as a pivot and put it into 2 buckets. And then you can take half from the left side, half from the right side, and then you'd get an array with the same median. Right? Does that make sense? So, for example, you have this array. You found the median. Let's say the median was here. And then you split it into 2. Why is pivoting split it into 2? Well, because it's the median by definition. And then I can take whatever at random. I can take, let's say, this half, and then let me take this half. And this is an array with the same median. So overall, the runtime of this would just be linear, right? So think order statistics.
If it were small, well, we truly only going to say if it were sorted.
Well, yeah, then you just do whatever, n over 4 to 3n over 4. Okay. Part number C. This one, I actually want to make it rapid fire. I'll give you guys maybe 15 seconds. Oh, okay, sure. So F is a flow. It's a mapping, right? It takes, for every edge, it gives you some value, some flow through it, right? It's a feasible flow. The value of a flow is just the sum of the flow out of the source, right? The value of the flow is max flow, if the flow is maximal, of course.
I forget, was it a condition of the flow to be, we have positive capacities only like positive?
Yeah. But keep in,
Zero capacities in the network flow?
well, a capacity 0 is equivalent to that edge not existing. Yeah, go for it.
It's true because the value of the flow is the sum of the flow coming out of the source, and that means that no flow is coming out of the source. Therefore, by conservation, none of the intermediate flows also.
Well, so this direction would be right. If the flow on every edge is 0, the value of the flow is 0. But if the value of the flow is 0, that does not imply the flow through every edge is 0. And here's an example. Okay, so I've received an answer for true. Can someone tell me an answer for false? Yes.
Like a cycle.
Mm-hmm.
Cycle would have one in it, and there's no flow coming out of S, but just a cycle.
Yeah, cyclic flow. So think of something like this. Sure, give it some direction. Why not? This is a feasible flow, right? Let's say these are the flows. All the capacities are 1. Then this is a feasible flow. The value of the flow is 0, but the flow through every edge isn't 0, right? A little tricky.
But there's no flow coming out of S. How could there be any flow in any of in the cycle?
Let's say I turn the tap on and then I just have this cycle of water running through these pipes and I turn the tap off. I just have a motor, generator, just cycling through this loop. Yes? Yeah?
That mean like all the nodes in the cycle also has like outgoing flow.
No, the definition of the value of the flow is just the sum of the flow coming out the source or the sum of the flow going into the sink. In this case, it's 0, right? So the value of the flow is 0, but the flow through every edge is not necessarily 0. Yes?
But then how is it one?
How is what 1?
Flow out of S.
One in, one out, one in, one out, one in, one out.
But if
It's all,
the flow out of S is 0,
yeah?
and the flow, if either of those is also 0, like capacity is 1.
Why not? A feasible flow, all it has to do is hold the capacity and conservation constraints, which this does. Yes?
I don't think we've ever seen anything where they like open it and then close it.
Mm-hmm.
That is correct, like we can do that for this.
Why not? This is, does everyone agree by definition this is a feasible flow? Okay, then that's it. That's the end of the argument. So when you're making claims like these, it's important to think of edge cases. Yes?
If we impose the fact that the capacities were non-zero, would it be true?
Well, the capacities were all 1 in this case. What I wrote out was the flow, not the capacities. The capacities were 1 in that example too. So no, it wouldn't be true. It would still be false. Right? The example I wrote was...
You had like coming out of like the start,
Yeah.
you had a capacity of 0.
No, that was the
Oh
flow.
no, wait, no, never mind. Yeah, no, that makes sense.
Yes.
Is VF just any flow, or is it specifically like max flow?
No, it's just some feasible flow.
Okay.
Right? Okay. Part number D. I'm not sure if you guys learned this. Did you guys learn polytime approximation schemes?
We didn't do this in class.
You didn't do this in class? Okay, can we all agree to skip part D? Apparently you guys haven't done it. Okay, good. Part D though, the answer, this basically says there's some max problem and assuming P not equal to NP, there's no polytime 1 approximation, but there is a polytime 1 plus epsilon approximation for any small epsilon. So you can get as close to, you can approximate as close to optimal as you want, but in polytime, but you don't have a polytime exact solution. And the answer for this is true, and it's 0, 1 knapsack. That's the easiest example. You can get as close to the actual optimal you want in polytime, but you will never be able to get true polytime unless someone proves P equals NP, right? Okay, part E almost ended up being on your final before I caught it. So yeah, take some time and do this one. This one was on the final before I removed it.
Why did you remove it?
Because I wanted to use it.
Even though you already said the answer, so I'm still unsure. Guessing this one.
Okay, let's wait on you to answer. Let's actually try and see if the class has deciphered what this means. Okay, hopefully everyone has read what the question is trying to say. Here's my question to you before you solve this. If you just look at the first 2 sentences, what kind of cut is C? It's a min cut. Amazing. So C is a min cut. So E1 through EK are all the edges on the min cut. Okay? Now the question is asking if for the min cut, all the edges that go from S to T, if I increase their capacity by 1, then does it guarantee that I increase the flow by 1 for each increase? So if there's K edges, I increase the capacity by K. Does that mean that the flow also increases by K? Okay? And I want you to think hard on this. Okay? Yes.
What are the edges? The edges are like going out from like the X cut to like.
Yes. So E1 through EK. So ST is a min cut, right? So you have S and T, and any edge where the tail of the node is in S and the head is in T. All of these edges are E1 through EK. Yes.
What does it mean when you say you have an ST cut with K edges? Like, does it mean like there's K edges coming out of S, or?
And well, an ST cut, S and T, this is not the source and sink, this is the sets.
Yeah.
A cut is a partition of the set of nodes.
Sure.
And the partition must have the source in one and the sink in the other, and the set, and the partition that has the source is called capital S, the partition that has the sink is called capital T. And the edges that have the tail in as one of the nodes in S and the head as one of the nodes in T is the edges of the cut, right? So for example, if you had a graph, and this is the source, and then you have like a sink, and then you have a bunch of other nodes. Any edge that goes from here to here would be, yes. Yes. What do you mean by inside of the cut? A cut is a partition of nodes, so you're going to have to clarify what you mean by inside of the. Do you mean something like? Do you mean like an edge like this, like something that's within S or something that's within T? Yeah, no, that doesn't count as one of the edges of the cut, right? Okay. EI equals UV, where U in S, comma V in T. Okay. I don't want to spend too much time on this, but this is something that you've sort of seen in class before, in some capacity. Raise your hand if you think this is true. One person. Raise your hand if you think this is false. A lot of people. It is indeed false. Can someone tell me why? Yes. Right, correct. So that's a really good intuition. If you change the capacities, that cut may not be min cut anymore. How I like to visualize this is bottleneck edges. Bottleneck edges are edges where the flow is equal to its capacity. Increasing the capacity gives it a chance to push more flow through. And what I want to mention is that the min cut is not exhaustively the set of bottleneck edges. There could be bottlenecks that aren't part of the cut. And the simplest example I have for you guys is this one. Source, some random node, U, and then the sink. And let's say the capacities are 1. Now there's 2 min cuts, one here and one here. But if I increase the capacity of any of these edges, it does not increase the flow, right? So for example, here's one cut, S and UT. And there's only one edge, so K is equal to 1. And if I increase the capacity, I get 2 and 1. But the bottleneck is still there. It's just somewhere else. It's not in this cut. And vice versa, by symmetry, right? So your cut doesn't necessarily contain all the bottleneck edges, and unless you fill all the bottleneck edges somehow, at least you get like one path, one augmenting path. You'll be fine. But here you don't have an augmenting, because if you have this filled in your residual graph, you only have a backwards edge, right? Okay. You just give this example and be like, regardless of what min cut you pick, if you increase the capacity by 1 on that edge, it doesn't increase the flow, right? Okay. So these were a little bit tricky. Now we're going to go on to the easier parts. I have one question for each sort of genre. I have greedy, I have DNC, I have all of it in order. So it's going to get a little bit harder as we keep moving, because the later part of the course is a little bit more difficult. In case we don't end up covering all the questions, what do you guys want to do? Do we want to take a poll on skipping like DNC? Do we want to take a poll on skipping greedy? What's the mood? Yes.
Well, what question do you expect to reach?
Well,
Expect to add?
well, it depends on how fast you guys can solve it. So I think we can do, so we have 6 questions. I think we can do 5 of them. I just have one more from last year that I've put on this time. So I just want to know what you guys prefer, like going over it in class or letting you guys solve it on your own and then seeing the solutions after, right? So raise your hand if you want to just go over examples and see understanding and insights. Okay, and raise your hand if you want to leave it for after. Okay, not a lot of people. Okay, so then we'll try and go over everything. Let me not yap and give you time to read this and solve this. Do not prove it. No proof. All right, just algorithm and runtime. Welcome, sir. Here, prize for being late. It's fine, you haven't missed a lot. We did one question.
Oh, nice.
Oh, this is 80% off at Old Navy. No, I'm just kidding. Yeah, this is Old Navy. I don't know how cheap it was, but it was pretty cheap. Yes.
Do we expect to see, like, given this set of constraints that the maximum and objective, perform the simplex method?
Okay, I've been asked whether or not you guys have to do simplex. Do I leak it or no?
Yes.
Of course, you guys are biased. I can't.
Flip a coin.
All right. Okay, I don't know what it says, but if it's heads, if it's heads, I'll leak it. I'd say you're fine without it. I think, but I do think you guys would have preferred doing simplex than the one I put on your exam. I don't know why you guys are worried about simplex. That's the easier part.
Flip it again to see if it's
No. Just a couple questions here and there.
Should be like a little M next to the questions so that we skip.
Well, I think you'll figure out what questions I've made. Sorry, what? Yeah. Is everyone okay to go over solutions? Raise your hand if you need more time. Okay. I'll give you 1 minute. 1 minute just for you. Okay. So for those of you who want to answer, 1 minute, formalize it. Formalize it in your head so when you talk to me, you sound very, very impressive. Thank you, sir. With you, now we have 73 people in this room. Okay. 1 time is over. 1 minute's over. Algorithm. Who wants to take a go? Yes.
Assuming we got the list isn't sorted, you sort the list.
Absolutely. Short list. Ascending, descending. Doesn't matter.
From least to greatest.
Sure. Ascending.
Yeah. Is n log n.
Mm-hmm.
And then, like, while the current element that you're on the list is less than the previous element plus 1,
Mm-hmm.
you just add the current element to, like, ui, where u is, like, an interval. Like, u is...
Yeah, you add the corresponding sort of like interval.
That's just, like, a linear time.
Yeah, just a run through of this sorted list. So that's O of n. Perfect. Great.
What's your midterm question?
This might be similar to your midterm question, but all greedy things that are like identify like overlapping or interval cover. It's usually like this. So one tiny step right above this. If it's empty, return empty. Right? And then sort. I also like to call this reindex. And this just means that, sure, you started with U1 through whatever UM, but after I sort it, I'm reindexing everything. So then it's again U1 through UM. It's just a different mapping, right? Then it's like easier to work with. Okay? So that's n log n. Is it n or is it m? No, it's n log n. Okay. And then you know that it's not empty, so you know you have to take the first element. And the best interval you can use takes that first element and puts it on the leftmost side, so you have as much cover as you can for the elements on the right. So you'd start your list with, let's say, x1 and then x1 plus 1, open brackets, and that would be your first elements. And then you can run a for loop, or you can do a while loop. Either or works. For I equals 2 to n, if xi is greater than equal to minus 1, 2 plus 1. This is, sorry, minus 1. No, wait, plus 1 is right. This is Python notation. I'm just saying take the latest interval I added and see its rightmost value. So that would be, wait, no, I've already accounted for that. Look at x1 plus 1 and then see if x2 is bigger or equal to. If it's equal to, I have to include it, right? Because this is an open bracket. But if it's within this range, I don't have to worry about covering x2. It's already covered. And I can move on to the next one. If it isn't, if it's on the border or if it's beyond this interval, then I need to add another interval to cover it, right? So if this happens, so L at minus 1 is the last element. 2 is within this interval. I'm just taking the second value, so the right-hand side. Then I want to add, okay, you guys might not be able to see this, but you want to add xi, comma xi plus 1. So you want to add the xi interval. And then once this for loop terminates, you just return L, right? What's the runtime of this? This for loop, this is just constant time. So the for loop runs in linear time. So the runtime is dominated by sorting, which is n log n. Okay, fair? Is everyone okay with this? If I have time at the end, I will give you like a sneak peek of what the official solutions look like. So, and then when I get home, if I have time, I'll give it to you guys as soon as possible. Okay, so this is just algorithm, and then I give you some space for running time. Okay. Any questions before we move on? No questions. Question number 3. Yes. Yeah, okay. Let me see if I can do something with my iPad. I wonder, it's weird I can't do the 50-50. It doesn't make sense. Well, did you bring enough to share with the class?
Sure, if you bring up salty.
Everyone will get one little bit.
Algorithm that shows So is the cost of going on a road that has a toll the length times the cost of the toll? Is that what the length is for?
No. The cost of it's like the 407. Do you guys know the 407? It's sort of like the 407. But the 407 is proportional to the time or length, but this is just a fixed cost. By the way, this is actually a fairly common thing in India. You have like these toll booths, and then when you enter the highway, they sort of register you, and then when you exit, you just get scanned and then money out of your bank. me set this up first.
Oh, length in miles. Yeah, I think that's all you can just say this is what the edge weights with the miles cut by cost or whatever. Yeah, and then
All right. Okay. Let's calm down, guys. Let's calm down. We're here for studying, so let's see. Do you guys need more time? Were you guys just discussing, or no? We're ready with this, right? Okay. Does anyone want to give this a shot? Yes.
You could use Dijkstra's.
Mm-hmm. Mm-hmm.
And you could add an extra constraint that in your priority queue you do not add an edge if the sum of the edges that you have so far
Yep.
exceeds your cost, your min cost. And if you do exceed the min cost, then you backtrack one node and then you do it again.
Well, then it's not Dijkstra anymore because then you're backtracking.
I was thinking this is maybe similar to the knapsack. Could you
Okay.
do the cost to the length of the path ratio? Or does that also not work?
So knapsack greedy?
Yeah. Does that work?
Well, you'd at that point you'd sort of be taking edges, but you can't guarantee that makes a path from Toronto to Vancouver. So that's going to be hard. Yes.
Modified Bellman Ford,
Okay.
where on each,
What does Bellman Ford do that Dijkstra doesn't?
it checks the distances, first it checks length 1, then length 2, and we don't want just the lowest cost. I think it says the shortest one that's less than X.
Yep.
So since it checks first length 1, then length 2, at every step we can say, have we reached this node which costs less than X? And if it hasn't, then just continue to up.
Okay. So you'd find the shortest path with one or fewer nodes, but you're looking at nodes, right? What if having a new node gives you a better outcome? Yes, that's longer than shortest, but along that path there's no tolls.
It says to find the shortest path that doesn't
Yeah, what I'm saying is, suppose you're looking at the shortest path that uses 3 edges, right? And there's a longer path with no cost of tolls, but you only looked at the shortest one. And then let's say the shortest one has too much cost, in which case you will reject and you'd move on, which you shouldn't, because there's a path with 3. That's longer technically, but it doesn't use any tolls.
Every step also checks if it's like greater than the cost.
Like, it's just a condition
I
that you have.
I doubt that works. And again, with the same argument, you're trying to keep track of too many things. What you want to do is somehow make the toll costs implicit, right? If you were to be able to modify the graph in such a way that the toll costs became implicit, and then you could just run simple Dijkstra or simple Bellman-Ford, right, on that modified graph, you'd be able to work out the shortest path. Yes?
For the shortest path, do we mean by miles or do we mean the least edge?
We want the shortest path based on the sum of the lengths. So yeah, the distance. It's using the length function we have over there. Yes? You could, but as I mentioned before, I've ordered these questions in a very specific way. Yes?
You just do Dijkstra's, but you replace the edge weights with the ratio of like miles divided by cost.
Okay, that's a good idea. That's a good idea. The thing is that the length truly doesn't have anything to do with the cost, right? So mixing the two it's like changing your heuristic on what you're trying to use. The Dijkstra is just a way to expand based on some heuristic, right?
What's the problem with keeping track of 2 things at once? Like, what issues do you
Too many combinations.
Too many combinations?
Yes.
Okay.
Yes.
I just what I want to ask is, like, question is, are we required to use like one method?
No, because we don't force you to. But one method is, the more obvious method is the one that is assigned full marks. And then if you're doing some convoluted method where an easier one exists, and it's something that you've sort of seen in class, then we do deduct marks for that. Right? So this is a tricky one, but let me just say this. We're going to go on break after this question anyways. This is probably the most important question here. Yes.
Can we augment the graph so that the lengths are 1, and then we divide the cost over that length? If we add 1.
So like change the graph, add some things at the end. Yeah, that might be a really good idea. Try to work on that. Try to build on that. So well, okay, but that doesn't really do anything, because then between any 2 nodes, you just have a bunch of other nodes and edges, but that's the only path you can take between those 2 nodes anyways, so you're back to square one, right? Even if you divide the cost. All right, all right, all right.
Can we accumulate the costs?
Yes, that's pretty much what you have to do to incorporate it. You need to modify the graph in such a way that in the modified graph you can tell when you took an edge that is like a toll edge, right? So yes.
Do you split each node into two, and then is that?
Yeah, you're on the right track. It's splitting nodes, having copies of the graph. It's all on the right track.
So I have 2 ideas.
Okay.
One is that you make an identical graph, but rather than keeping track of the like the weights, you keep track of the costs. And then the other idea is just to use DFS on the costs and then run Dijkstra. But that's probably like too many combinations.
Exactly.
So I think the first one is better if it does work.
Okay, but if you run Dijkstra on the cost, you'll just find what?
The minimum cost.
Well, we see that most of the costs are 0. So it's going to probably give you a 0 cost path, but it's going to be like through none of it. Right? So, yes?
Use like that for search and then like just throw away all the nodes that like requires like more than X to reach, and then like the modified graph, and then just run Dijkstra on the modified graph.
So brute force. Yeah, I don't think that's probably the right way to go. Yes? Okay, copy of the graph. You're on the right track. How many copies? Okay. Okay, so you have the original graph, and then you have the copy, and then you want to do what?
In the copy graph, remove edges that have a cost.
Okay, no toll edges. Okay,
And then you call Dijkstra's on the first one like you normally would.
sure.
You would, as soon as the cost exceeds X, you switch over to the other graph at that same node,
Mm-hmm.
and then you just run Dijkstra's on.
Yeah. So that's correct. Almost. What your algorithm will do is it will find the shortest path where the cost is as large as possible but doesn't exceed C. Or doesn't exceed X. Right? What if, so what he will find might be the shortest path that, let's say you don't want to spend more than 100 cents. Then he might find the shortest path that uses 99 cents. But what if there's an even shorter path that uses 65 cents?
An even shorter path, then wouldn't that be hard?
No, because let me work this out. But let me tell you, you are definitely on the right track. You want to make a copy, somehow make it implicit. And this transition that you're talking about, that you switch over to this other graph, you can't really do that directly in Dijkstra. Like, how would you're doing Dijkstra, right? And so somehow you're keeping the track of the shortest paths. And let's say simultaneously you're also backtracking to find that shortest path, and then you're also having like a cost matrix associated with it. When do you actually switch over? When the distance between Toronto and any node exceeds C, you just switch over? Or do you wait for you to get to Vancouver and then you switch over? When do you switch out?
Switch over when the cost exceeds.
Which cost?
The cost of the path that you're currently on. Like you keep.
Well, Dijkstra keeps track of every distance from one node to everything. So which one?
The shortest one.
Shortest one to where?
From where you start. As Dijkstra would keep track of.
Yeah, from S to, let's say, A, B, C, D, and none of them are Vancouver. And if SA exceeds whatever X, do you just switch over?
I think I see what you're saying. So like it's possible to go back and maybe choose a different one and then continue.
Maybe. But let me present to you basically what I have is a lot of copies of the graph. Okay? So I have, not k, sorry, x, right? And essentially, I have these copies, and I'm going to connect them somehow so that whenever I take an edge that is some cost, I jump accordingly to, some graph on this point. So for example, if I take an edge that's cost 7 from G2, that edge I take should land me somewhere in G9, right? And then this implicitly takes care of all the costs. Okay? So k copies, and for all I comma j where j minus I equals the cost of an edge, for all edges, add u I and v j. So this is a little convoluted, but all I'm saying is for all the costs, for all the edges that had 0 cost, the copy has the edges within itself, right? So for graph 0, which is my original graph, any edge that has a 0 cost of the toll, I just keep the edges there. But for any edge that has a cost, let's say if I have like a cost 3 between nodes u and v, then I connect g0 or u0 correspondingly to v3 here, right? And so I move. And not only do I have to do that for 0 and 3, I have to do it for 1 and 4, and 2 and 5, and 3 and 6, and so on and so forth.
What do you connect it to? Exactly the start of the other graph?
No. For every, so when I say make copies, every graph had uv. Let's say it had the set of nodes u, u1 through un. I have, now I label them based on which copy they are as well. So I have this index. So any node uv that was in G0 with cost 5, I now have a u0 connecting to v5 in that graph. So it still represents where you are, but it also incorporates the cost. Yes?
But I don't understand what you mean, like, is all the copies the same from these groups? Yeah.
So let's make it simple. Let's say you have u, v, w, right? And then I have, so this would be, now I would add indices, u1, v1, w1, and then so on and so forth. And let's say the cost between u and v in the original graph was 2, right? So then I would connect u2, v2, w2. I would connect u0 with v2. And this edge would no longer exist, right? None of these edges would exist. I only connect them, the tail to the head, in some other copy, right? This edge would only exist if the cost between them was 0, right? So which copy you're on sort of indicates how much money you've already spent. Does that make sense? Okay, cool. So not only would I be connecting u0 with v2, but I would also be connecting u1 with v3, right? Yeah, their length is identical to the length of uv, right? So it keeps track of the distance as well. Okay, what's the problem here? I definitely have one starting point, right? Toronto, 0. This is where I haven't spent any money. I just got into my car. But now I have so many Vancouvers. I have as many Vancouvers as there are copies. So what do I need to do? I need to find the shortest path from T0, from Toronto, to what? Which Vancouver? Well, technically, we don't even care about minimizing. We don't care what the cost is as long as it's not exceeding x. So we actually have to take the shortest distance from Toronto in the original graph to every single Vancouver anywhere, right? So for example, if we look at the shortest path from T0 to Vancouver here in G2, it means that's the shortest path that uses 2 cents, right? And then similarly, for any path, any shortest path from T0 to, let's say, VI, that's the shortest path from Toronto to Vancouver that uses exactly I cents. Does that make sense? So this is sort of brute forcey. Yes? Yes, you raise your hand, right? Yeah. So let's not use I, let's use C. So, like I said before, you have copies of the Vancouver node in every single graph, and you compute the shortest path for all of them. And for example, if you were looking at a particular V star alpha, then that's the shortest path that costs exactly alpha cents, right? Think about this. What if there's a direct highway from Toronto to Vancouver, and its cost is whatever, 100 cents, and then there's some cheaper ones. Then if I have, then G0 to G100 is from Toronto to the Vancouver one in that copy, in the 100th copy, will tell me that that's probably the shortest path because it's a straight line, right? But anything before that, we will not even see that edge there. We won't even consider it. So we would not even know that exists.
I just want to make sure that I understand the copying correctly.
Mm-hmm.
So each graph will have a copy of all the vertices.
All the vertices.
Each edge will only exist
according to
either
this
in
rule.
one graph or between two graphs, right?
Yeah.
So no copies of edges.
Well, this procedure I have for all ij for all edges sort of generates a bunch of edges, right? So for every edge that was in the original graph, I actually do, it has a cost, and then I find every single pair I and j where the difference between the two is equal to that cost, and I add that edge. So technically, I have about as many edges. The edges also multiply by the number of copies, right? Yes?
But how can you tell it's the shortest path from
What do you mean? It's the shortest path?
But like, how can you tell it's the shortest path? The top of the
Oh, we just take the minimum of all of them. The shortest path from Toronto to Vancouver, with at most 100 cents used, is equal to the shortest path with 0 cents used, or the shortest path with 1 cent used, or the shortest path with 2 cents used, so on and so forth. If I split it by the number of cents used and I compute the shortest path for all of it, and then I just take the minima, I find the shortest path overall. That doesn't exceed 100 cents. Yes? I'm sorry, I can't hear. Guys, can I get you guys to calm down? I can't hear students.
So can all of the Vancouvers just have like a zero cost edge for like final Vancouver, and then like the path is just to final Vancouver?
Well, it wouldn't make a difference, would it? But yes, you could. You could do that. Then it would just be like one graph, and then you would just look at it through there. Yes. You raise your hand.
Oh, me?
Yes.
Can you give us like a more easy example, like actually like a few cities and then Toronto next to it? I really don't get it, what you're
Okay. Let's do it. Sure. Anyone know what's here in the boonies? Some city?
Edmonton.
Sure. Well, Edmonton's is over here, but. Okay. Sure. I don't know where Winnipeg is. I have no idea. Okay, so, and then let's say, yeah, 0, 0, 0, 1, 3, 7, 5. Sorry? No, I haven't even given you the x. Sorry. Okay, so let's say you have this graph, right? Okay? What you would do, I can't even move this, is you would make 7 copies of t, you would make 7 copies of w, so you'd have these 7 tiny copies. How would I draw this? So let's go about it this way. Copy 1, copy 2. Maybe I should not have, sorry, not 10. I would need 10 copies. Let's bring that down a little bit. These are the costs. Damn, I need the distances. Sure, all of the distances are 1. In which case, this would be the best one. If x is not this, right? But, okay, you would make 5 copies now. That's a little bit better.
Well, if all of them were the same, then you could just let us know the extra.
If all of the costs are identical?
All the lengths, right? Either one. Like, if all the costs were the same.
No, it would still, I think it would still be different. Okay. 5 copies. And so Toronto to Winnipeg has cost 0. So for every pair of Toronto-Winnipeg, the edge only exists within its own copy, right? So you have this Toronto-Winnipeg everywhere. Let's call this 1, 2, 3, 4, and 5. Actually, I should be using 0, 1, 2, 3, 4. And you would have k plus 1 copies because you need 5. Right? But for this edge from Toronto to Edmonton, the cost is 3, which means that this t connects to the Edmonton at number 3. Like this. Right? And then this t connects to the Edmonton on number 4. And then this t connects to the Edmonton over here. Implicitly, what this means is if you ever, in any path, take the Toronto to Edmonton edge, you will go from copy I to copy I plus 3. It's impossible otherwise, right? Because the only edges from Toronto to any version of Edmonton skip three copies. So then the index tells you how much money you've spent up until now, right? Does that make sense? Okay, cool. Runtime analysis, I will skip. Let's take a break till 11:30. Oh, you can do a runtime analysis. Yes, sorry. I have the runtime analysis for you alongside question number 4. Okay, hopefully everyone can see the question. I've written down the answer already, so I don't want to scroll down.
Just a question, what type of question was the last one? What did you count that?
So Dijkstra is what? Dijkstra is divide and conquer, I think. I have to check. It's on. Oh, whoops. I think it falls under DNC, at least on Anna's lecture tab. Let me see. Yeah, it should be greedy. It is. Where's the greed?
I don't see relaxation as a greedy operation.
Mm-hmm. There has to be something we're doing greedily. There has to be something we're doing greedily. Oh. Whoops. Oh no, just forget it. Just hold on. Look at this real quick. I got a glimpse. Well, when there was like a little bit, you know. Yeah, exactly. Yes.
Should the solution be better than n log n?
Yes, it should. Right? You could trivially just sort it and then figure it out, but you could do something better. It's an ordering.
Ordering?
Yeah. Of the array, B.
So why didn't you just say return sorted array or like the array?
What array? You're just returning B as is? That's not wiggly anymore. It's not wiggly anymore. You take an array and you want to reorder it so it's wiggly. So how would you do that? You can't just return the original array.
Oh, so you just return it in place. Is that what you mean?
Doesn't matter if you return it in place or not. A permutation just means a reordering. So 1, 2, 3, 4, and then I could look at 1, 2, 3, 4, and then I could flip a coin, and then I could do 3, and then 4, and then 2 and 1, and that's a permutation. Yes. Are the numbers distinct? No, they don't have to be. The fastest one possible. Okay. We're going to get started. You seem like you have an answer.
Find the median and then like look for being smaller on like odd numbers and everything bigger on even numbers. And
Yeah.
median that's last value.
Yeah. That's essentially the same. It's similar to what we did earlier. You would find the median, and then you have all the elements that are smaller than it, and then all the elements that are larger than it. You would take your first element to be the median, and then you want what? Less than or greater than? You want less than. So you take something from the right, put it there. You take something from the left, put it there. Something from the right, something from the left, something from the right, something from the left bin, and then that's it. You'd have a wiggly array, right? So that's it. This is the algorithm. You do deterministic select in linear time to find the median, you partition in linear time on the medium, and then you alternate between elements from both buckets, right? Because you started at the median, and you know you have, on the less than bucket, you have smaller things. On the right side bucket, you have larger things than this median. So then start with median, grab something that's larger, then grab something that's smaller, grab something that's larger, and just repeat until you have your entire permutation, right? So this is a linear time array. Another less efficient one would be to just sort it and then do the same thing, where you would take the smallest and then the largest and then second smallest and second largest and then that way. Yes, and then you. Whatever order statistic algorithm you saw in class for finding the kth element is, there's two types. There's R-select and there's D-select. And they differ on how you're picking the pivot in order statistic. But just say find the median using order statistics, that's still fine. Yes. Wait, sorry, you had a question. You first and then you. It better?
Not better, but a nice divide and conquer approach with one merge step, where you just, let's say you're at your list of size 1, you just put the smallest before the smaller one before the bigger one, and then when you're merging the lists of size 2, you would arrange them to keep the wiggly going.
Well, how would that be a constant time?
Because you would just concatenate them either on one side or the other. Or could both values.
That might not work. And the merge step would be linear time, which would again make it n log n. It would be proportional to the length of the merge components. But yeah, this is one way of doing it. You had something to say?
Just in general, any ordering in arrays, order statistics is that first go to?
Yeah, order, median, order statistics should light up first. So yeah, there's that. By the way, what kind of algorithm is order statistics? It's divide and conquer. So you're on the right track. It's just this is like an easy abstraction of what you might be thinking, right?
Is this pseudocode for
No. What the solution I will give you, which I've written out, typed out, that's full marks. All right. This is whatever I was able to write right now. All right. Runtime. Every step is linear time. The runtime is linear time. This is full marks. Yeah, we've got a bunch of time to spare. Oh, brother. Um, I think the example you can work out. It's 1 through n, so there's no 0, 0 at all. So 1, 2, 3, 4, 1, 2, 3, 4. No, you can leave some columns empty. For example, if on on an entire column all the values are negative, it's always a good idea to skip that column, right? All right, let's talk about this. So, hopefully you guys have read what the problem is. You have some checkerboard with values on it, and you're allowed to place pebbles on it under certain rules. You can either have one pebble on a row or column or none. And if you put a pebble on any particular spot, then one of the following must be true. The pebble on the next spot, if it exists, has to be either this diagonal or this diagonal, right? Okay. So there's sort of a rule on how you can place pebbles, and your score is essentially the score on the checkerboard where you've placed all the pebbles. You add them all up. That's your total score. We want to maximize this, right? So based off of this, part A says, identify subproblems. What's the easiest way to induce a subproblem? Right now, this is just one big problem. What's the easiest way? We've seen this in class a lot of times where you have matrices or arrays. You do something about it. What is it? Sure. That's like cases, but like earlier, how do we induce subproblems, like certain things? How do we induce that?
Suppose you want to find the optimal solution for p pebbles.
Yeah.
You would want the optimal solution for p minus 1 pebbles.
Mm-hmm. But is there a certain way that we can break this input down and go through it systematically? Yes. Yeah. So the easiest way to introduce subproblems is to introduce order, right? And so what you can usually do is you can introduce some sort of order. Let's use J or something, and it's just like column number. So now I can somehow relate to the optimal pebble placement of using all 4 columns to somehow the optimal pebble placement that only uses the first 3 columns or the first 2 columns or something, right? Something smaller that only looks at part of the input, right? So subproblems refer to working on subsets of the input, and if you introduce order, that's a very easy way to partition it and where the subsets sort of grow naturally, right? In this case, we chose column. It could also be rows, but column seems a little bit more intuitive. Can someone tell me why column would be a little bit more intuitive? Yes?
You can only do 1 pebble per column.
Oh, well, you can also do 1 pebble per row at most, so.
No, you can do it.
Oh, whoops. Yes. Okay, good. Then that's the right answer. Okay, that would make it too hard, no? if you could do it, never mind. Okay, so yeah, then of course column-wise seems to be more intuitive because there's order there as well, right? But we also need something else because it's a matrix, it's not an array, right? So sure, the optimal placement using the first j columns plus what? We need to force something else. Otherwise, there's way too many combinations for us to handle, and the base case will be massive. Or the recurrence formula would be massive. We might need to force something as well. Yeah, we might need to force. So OIJ basically says the best way to place the pebbles using the first j columns, where on the jth column I'm forcing the pebble to be on the ith row. So I'm forcing I comma j, right? So if it's 2 comma 3, I'm forcing from the first 3 columns, I'm forcing that I take this 3 and I put a pebble here. And then I try to find the recurrence relation. If I know there's a pebble here and I'm only allowed to use these 3 columns, what's the best I can do, right? And that's where you're going to have to start finding recurrences. Now, here, there's a small problem. The rows go from 1 to n, but you're also allowed to not put a pebble, right? So somehow we need to include that as well. So can we just have some convention for that? What's the easiest convention? Yes? No. The act of not placing a pebble actually impacts on what you can do previously, right? If I don't place a pebble on column 3, I can actually pick anything for column 2. But if I know there's a pebble on column 3, it restricts on what pebbles I can place on column 2, right? So we need some sort of convention that allows us to handle the option of, or gives us the option of not putting a pebble. And for me, I'm just going to say when I is 0, it just means that I didn't put a pebble on this column, right? It's just convention, right? So I equals 0 means no pebble. Yeah, and rows go from 1 to n. So when I say I is 0, that means it's like over here. I put it here, right? It's not on any column. There's no score to be computed, nothing. Okay, sure. And then there's some sort of base case we have to handle. What's the easiest base case we have? No, in terms of j, like what's the smallest j we can do? 1, and what's even easier than that? 0. What's at 0? What does it mean? I have nothing. I don't have a board, right? So j equals 0, no board. Okay, so then now you have this OIJ where I goes from 0 to n, j goes from 0 to n. And your next step would be to define this sort of recurrence relationship. I think some of the base cases are kind of easy, some of them are hard. Yeah, absolutely. I will be giving you time to do it. There we go. It's just whatever I said over here. All right, let's have you work on the recurrence. I actually gave you the base cases over there, so. Oh. Right. OIJ. Well, it says over there, it's the max score using first J columns and Pebble on IJ. It's the score that we're keeping track. Yeah, we're keeping track of the score. Yeah. And you're only using the first J columns. Yeah? Cool. Okay. Okay. Do we need more time? Okay. More time it is. Yes.
Why do we need all those base cases, like if we're restricting like the matrix to go from 1 to n?
Not really. You could have skipped this convention, but I like having the option to just like handle everything. You know, just extra sure. You can start your base case with j equals 1. It's fun. Oh, wait. You can't. We'll talk about it. All right, I'm going to ask again. Are we confident on having like a good idea? No? Okay, a little bit more time? Yeah? Fine.
If we wanted to go the row, like this is tangent. If we wanted to go by row, could we do like a divide and conquer DP type of thing where we divide it such that we don't end up with 2 tuples on the same row? Then you DP on each of those smaller subproblems, and that ends up being like reducing to something like this.
And
then you aggregate it.
I think if this rule applied both on rows and columns, you might have to do something like the 1 by 1 and then the 2 by 2 and then the 3 by 3 and work like that. I think that might be the trick. Maybe. Okay. Hint for the recursive formula. There's only 4 cases. There's 2 variables and compare them with 0. And every possible case, just handle it, right? So you have I and j, and they are either 0 or not. So there's 2 options here, 2 options here. There's 4 combinations. Figure those 4 combinations out. I've already given out 2 of them. Okay. Unfortunately, I'm going to have to get started on this. Yes, you have a question for me.
So just be I is 0, but your j is not 0, right?
Yeah.
So then, in that case, you haven't placed a stone in. Right?
You haven't placed a stone on or a pebble on column j. Yeah.
Well, would you have placed a pebble on column j minus 1?
Well, OIJ is the maximum score, so if that maximizes the score, why not? I equals 0 just means whether or not I haven't placed a pebble on the current column. Right? I'm allowed to do whatever I want for the first j minus 1 columns. Okay, so I'm going to have to get started. So yes, you wanted to tell your recurrence.
So 1.
Yeah.
And we place a pebble, so I is not 0.
Yeah.
So we look at the max between the optimal solution of
First j minus 1.
first j minus 1, the two diagonals.
Yeah.
I plus 1 and I minus 1.
Almost. Well, there's one other case.
There, as in the recurrence?
Yes.
Yeah.
So I minus 1, I plus 1 backwards,
Yeah.
and then one more.
0?
0. You can also choose not to put anything on the previous pebble too. What if you have multiple negative columns in a row?
At least negative. Right, okay, true.
Okay, and then one more case.
For the last one, it will be, so we're going to place a pebble on J.
Yeah.
So the optimal over all indices of I.
And 0.
J minus 1 and 0.
Yeah.
And I don't have
Yeah, because, okay, that's perfect. That's amazing. Here's your candy. Sorry. So there's 4 cases, like I mentioned. And the first 2 I've already written out. If I don't have any columns and I don't have any pebbles, I have no score. If I don't have any columns and I want to put a pebble on a non-existent column, it's just not possible. This minus infinity, this will actually never come into play. This is just for completeness, essentially. If j is greater than or equal to 1, so you're looking at some set of columns, and I equals 0, that means you put no column on that, no pebble on that column. Does that restrict where you can put the pebbles before? It doesn't. There's no restriction. So what do you have to do? You have to take the max of every possibility of the first j minus 1 columns, right? Because there's no restriction on where you can place the pebble on column j minus 1. So you have to take the largest over all possible placements, including 0, which means you skipped column j minus 1 as well, right? If you are forced to place a pebble, so you have a pebble on the jth column, then according to the rule of the pebble placement, it says I can only, if I place a pebble here, I can either go diagonally forward or like up or down, right? The same thing if you work backwards, that means if I have a pebble here, then there must have been a pebble on the top left or the bottom left, right? So that would be the 2 cases. And the third case would be that you left the previous column empty as well, right? So this is a real, we'll talk about what this is on the bottom, but essentially I'm saying under this restricted constraint of the first j minus 1 columns, plus whatever the cost, because I put the pebble on ij, so whatever the weight of that is, I have to add that. On the bottom, this is just a fancy way of saying iterate over all possible cases of the previous column, so top left, bottom left, or not placing anything. This intersection just makes sure that it handles the first and last rows. So if I plus 1 is over n, this just makes sure that we don't include it, right? So we sort of do an intersection with this. This is a set, by the way. This is just 0 to n, right? It's a set of all natural numbers less than or equal to n. So if anything exceeds n, then you can remove it. Same thing with I minus 1. You'll never go below 0. Okay. Questions? No?
The last case, do we need max between that and 0 as well?
I included the 0. 0, I minus 1, I plus 1. That's the only 3 cases.
So it would be the base case.
Yeah, O, 0, j minus 1, where I didn't place it. Okay. If there's no question.
Wait, do we have to handle when ij is negative?
No, because according to you have exhaustively handled all possible cases, right? You also added the convention of I equals 0 and j equals 0. So there's no case where I is less than
No, I'm saying
0.
the weight of ij is negative. Like for the last case.
Well, okay, sure, it might be negative, right, for that particular column. But your OIJ stands for the max score where you place it. So you can't do anything. You placed it there, right? It's part of the subproblem. So if it's negative, it's negative. You can't do anything about it, right? Okay. If there aren't any questions, there's a pseudocode component of this, which I will be skipping because my typed solution will do it a lot better than I can do right now. Okay? And this is your pseudocode. Handling the base cases and looping over the remaining pairs. It's all quadratic. You essentially have sort of like a matrix, ij, and you're just filling out column-wise the values. And then what do you want? You want, what do you actually want at the end?
You want,
The j needs to be n for sure. Max, right? Max of I from 0 to n. The best possible thing, right? Okay. So that would solve the original problem, and it's all linear time. Space complexity is also linear time if you have a matrix. But if you realize, if you look at the recurrence formula, you only need the previous column to compute the next one. So you don't need to store all the values. You can just get away with 2 columns, right? So that way you can bump down the space complexity. So you were right. You just need the previous column, which means that you're fine with not having j equals 0 as a base case. Yes?
In the third case, why do we have to take a max of 0 to k to n? Shouldn't we just take this max of 0 to k to i?
To I is just specifying whether or not you placed a pebble on the jth column, right? But this k is talking about where you place the pebble on the previous column.
Explain the third case because I just don't understand it.
Okay, sure. Where should I do that? Let's just do it here.
could we have wrote the third case as like max from 1 to n and then 2 terms, that and 0?
That would just be that, no?
That would just be that. Yeah, just set it.
Yeah. So this is for you. This means, let's say this is the jth column, right? I equals 0 means no pebble, right? What does this mean? I have no restrictions on where I can put my pebble here, right? Can be anywhere. Can be anywhere. Or can be nowhere, right? Can be nowhere. I can choose to not put a pebble as well on column j minus 1. So I have no restriction. So the best thing I can do, I'd have to iterate over every possibility and pick the greatest one. So that's what this k iteration does. K equals 0 means don't put a pebble on column j minus 1 on the previous column. And then k equals 1 through n means put a pebble on whatever row 1 through n on column j minus 1. Does that make sense? Nice. Okay, any other questions? Nope. Runtime is quadratic. And the solutions, I'll give you guys a sneak peek before. So you guys will be able to handle that. Whoa, whoa, whoa. That's why I don't like that. Let's move this. I'm legally blind. I apologize for the wall of text, but it's fun to make a setup, so.
For the previous question, is it plausible to go from 0 columns upwards if I just swap the optimal to plus? Like, you know how we were working with j minus 1 before? just change it to j plus 1? Is that
So right now, our iteration is going from left to right. You're saying whether we can go from right to left. Same thing.
okay? As
Will
long as
work.
I just switch all the signs to plus.
You have to handle it accordingly. It doesn't matter which direction you do the iteration. You're fine.
Cool.
Okay. I'm not taking up the answer, but I do want to just give a breakdown of what this looks like if you were to draw it out. So graphically, you have k entrances and k ending points or exits, and then you have a bunch of other nodes and other edges in between. That's the estate where, you know, Billy is taking you on a tour for. Additionally, every edge has a weight, and the weight represents the duration. It's not fully relevant for the rest of the problem, but it is relevant for part A. And yeah, that's it. The goal is to find, okay, actually, someone tell me what the goal is. This is like some application of somewhere where we've seen this in class quite a bit.
It's an application of disjoint.
Yeah, edge disjoint paths, right? Good, good. So then try to figure out why Billy's idea doesn't work. Yes.
Don't share any two edges. Is that at the same time or overall the whole time?
Ooh, good question. So if you're, yeah. So there could be a harder version of this question where you're allowed to use the same path as long as the two, cars have certain distance or certain time between them. We're not focusing on that. We want like completely edge disjoint paths because the other one's too hard.
the vertices are connected by one-way roads, does that mean that the B1 to B3s are connected? As in B1
No, the exits aren't really connected, and the entrances aren't connected, but it's a directed graph. It just means it's a directed graph, nothing more.
When I see this, like I want to have nodes in the middle of the estate, but like nothing is mentioned about like what's. Like,
Yeah, you can have as many nodes in between. Yeah, just whatever. Whatever you want. Okay, do we have a counterexample? Anyone? Okay, can there exist a counterexample with k equals 1? No, right? As long as there is one path from some start to some end, which otherwise it makes no sense. Who would live on an estate where you can't leave? So yeah, k equals 1 doesn't make sense. So we need at least 2, right? And the trick is to see what Billy's actually doing, and he's finding all pairs shortest paths. And the problem with this is all pairs shortest paths doesn't care about using the same edge, right? It's just finding the same thing. So if we end up creating a graph where all pairs shortest paths end up using the same common edge, then that's a problem. And that's what our counterexample would be. So something like this. Let's say there's only one edge that sort of connects these two. Okay, but this isn't really a counterexample. For a counterexample to exist, we want Billy's strategy to not find it, but our strategy to find it. So we actually need 2 ways to get from, the start to end. So, but it can't be the shortest. So just put some large number there. So what's the problem now? There is a way, A1 to B1 directly, and then A2 to B2 using this path, right? What will Billy do? Billy will find the 2 shortest pairs, well, all pairs shortest paths, and all 4 of them will use this UV edge. So he won't be able to split them apart after, right? Cool. What?
K equals 3, we just copy that.
You don't even need 3, actually. Just k equals 2 is...
Oh, k less 3.
Yeah, you just found an example, right? So 3 doesn't even matter. Okay. Yes.
Doesn't he say that he's not going to pick 2 paths that share any edges? So like, why would he pick those 2 pairs?
Well, he can't. If he does all pair shortest paths, he gets 4 paths, right? From A1 to B1, from A2 to B1.
With the condition that he doesn't pick paths that share edges.
No, he first finds all pair shortest path, and then tries to select from that set of paths k of them that don't share edges. And it's impossible to do that because all 4 paths, all 4 shortest pair paths use edge E. So it's impossible to have 2 that are fully edge disjoint. So his algorithm will fail. He will return that it's not possible when in fact it is. Right? Yeah, well, I've been doing this for what, 2 years? Cut me some slack. But yeah, if you have suggestions on how to improve this document, I will greatly appreciate it. Okay. Max flow, I'll get you guys started. What's the easiest thing to do first?
The source behind the entrances with a sink at the end of the exits.
Yep, okay, step 1, add a source and sink. Source connect to all entrances, sink connects to all the exits connect to the sink. Okay, sure. And then the rest we keep the same. So we have the graph. Now we need what? We also have the source and sink. We just need the capacities. What are our capacities? Yes.
We need to find edge disjoint paths and make all the capacities one.
Yeah, exactly. This is literally just k edge disjoint paths. Whatever algorithm you learned in class, copy paste that. This is the same thing. So set all the capacities to 1. Find the max flow. If the max flow is k, by the way, if the max flow is k, because there's only k entrances, right? So the maximum max flow you have is k. If it is k, then it's feasible, and you have just whatever DFS, BFS, remove it, DFS, BFS, remove it, keep going, and you'll get k edge disjoint paths, right? If it's less than k, then it's just not feasible, right? And that's it. Ignore edge weights, have capacity 1 for all edges. Add source, connect AI, add sink, connect from BI. That's your flow network. And then the algorithm that uses it, we've already mentioned. Check max flow. If so, DFS on F star. Find all ST. Edge disjoint paths, right? It's not exactly DFS. Oh, yeah, well, DFS on the flow, I guess. Because any edge that in the graph that has flow 0 under this max flow, just remove it. So then you only have the ones, and that guarantees it. So then actually you can just DFS. It's quicker than keeping track of.
Should we rewrite algorithms we learned in class, or can we just?
No, you can skip it, right? So like for over here, I will literally, this is very poorly written, but step 1 would be like run max flow on the flow network you just created. That's it. That's all you have to say, right? You don't have to write out anything. Okay, runtime analysis. What did you do? Well, you had a graph with some nodes and edges, and then you added 2 more nodes. So nodes went up by 2. You added a bunch more edges. You added 2k more edges, right? And then you have capacities, and then you just run max flow. And that will be the dominating thing. So you can say runtime is dominated by, yeah.
And all those edges have
Ford Fulkerson.
as a capacity.
Yeah, because that's the trick for edge disjoint paths. What this means is our algorithm does not care about how long it takes, right? As long as there's ways to take them separately, right? And Billy wanted to just run people through. He thinks it's a numbers game. So as many people he can get through as quickly as he can, he just has more potential buyers, right? So he was focused on minimizing the distance. That's why he did all pairs shortest path. But it doesn't really work. Yes?
Can we guarantee that DFS won't find a path that interferes with multiple other paths?
Yes, you can, because when the max flow is k, when the capacities are 1.
I know we have k paths, but then I'm pretty sure there was that one assignment question which said, can you find a path that blocks off a bunch of other paths? Right?
If that would be the case, your max flow wouldn't be k, though.
Are you sure?
Yes. Because you're doing a DFS on the flow, not on the original graph. You're doing DFS on the flow. So whatever in the max flow, whatever had flow 0, you remove that edge. So you don't worry about anything. Okay.
Do you have a max flow to LP or the other way around, ILP problem?
You have some sort of LP. You'll see it.
Or can we do it since we're done? The questions?
We're not done. We have one more.
Oh.
We have LP. Okay. I don't worry about that. Let's skip that. Okay, part C. There's one more part to this. Billy realizes that just having edge disjoint paths is not enough. What if they meet at the intersection, right? What if I said, hey, I'll give you a private viewing, just you and me, and then you literally see my chauffeur driving another, just like Prince Philip's, just like across, and you're like, dude. So what do we want? We need to make sure that none of the nodes are common either, right? How do you do that? It's a simple modification. Yes?
You turn each vertex towards the 115.
Yeah, with capacity 1. So the trick is to split a node into two, have capacity 1. So this new graph, whenever a flow happens through it, you can only have one flow through it. So that means only one person actually uses that pair of nodes. That's it. That's that slight little modification. Split nodes into in and out. Don't write it like this. Wait for the solution. Okay. Yeah, don't worry about that. But okay, this is your last question. This is your LP. No, it's just I feel like Aaron would own a company. So I keep forgetting to give out candy, so if I missed you, if you've answered, please just raise your hand. Yes, there you go. If you've answered more than once, you can keep your hand raised. But don't lie, because I'm going to review the VOD, and I will send you a charge back for whatever 46 cents.
Thank you.
It's crack. This is literal crack. Wait, I can't say that. It's on. My name's Aaron. Okay, has everyone read the question? Yes? Is there anyone that's still in the process of ingesting? No? Cool. I will try and reformulate this into like what I think is easier. There's like a sequence of jobs and each of them have some certain duration. So let's represent this as durations, right? And you have like sequence of jobs, whatever. And essentially, you want to sort of partition this sequence into certain things that whenever you do a partition, you can only partition on sort of like an end, right? Because you can't leave a task halfway through. Someone else can't start a task halfway through. So you're essentially like selecting a bunch of tasks, right? So in the first shift, I can do 1, 2 tasks, 3 tasks, 4 tasks. I can do as many tasks as I want, as long as it's within the shift duration, which is H hours, right? And then I can do it again, and again, and again. And sort of I get this sort of different shifts. And I want to minimize the number of shifts that I'm using, right? Does that make sense? Is there a greedy solution to this, by the way? Do we think there's a greedy solution to this? Yes.
Just do this similar thing as on the midterm and the previous question.
Yeah, like taking as many tasks as you can within H and then repeating. Maybe that works. Unfortunately, that's not what the question's asking, so it doesn't even matter when you're thinking about it. So, how are we actually writing this down? We need variables, right? What could our variables be? Yeah.
Yeah,
You,
AIJ for the assignment of shift 1.
shift I to.
I to up to J task.
Okay, that could be one. So Xij, task I done in shift J or earlier, right? Okay, sure. Can we make this even simpler? Yeah, why earlier? Sure, we can just force this. Xij means task I was done in shift J. Okay. So then, fine. What are we trying to minimize? Yeah. So what would our objective function look like if we just had this? Minimize over what? Like we only have these variables. We need a linear combination of these variables somehow. Yes.
Do the people work, like let's say, there's a gap between, like there's not enough time to do another task.
Yeah, they
Do
just.
people still finish their shift doing nothing?
Mm-hmm.
Pretty much just like an exercise,
That's all of us though, no? At like 3:30 on Friday. The next scrum's on Tuesday, so why would I care? We're trying to minimize some linear combination, but it's tough because if we do just like a summation xij or something, right? We'd get all the i's as well. And we don't know how many i's are happening. Yes.
Can we have the sum of xi, j with the same j's is smaller or equal to n? Like the sum of that is smaller or equal to n. So
Well, actually, your objective function doesn't have an inequality. It's just a function, a linear combination of. Yes.
Do we have another variable?
I like that. What does it do?
Is how many shifts there are. So for
Just y is 1 if.
one if it is.
Okay, yj. Shift j.
There's a task assigned to us.
Yeah. Let's call it utilized. Shift j is utilized. Sure. Now is it easy? Well, now what are we trying to minimize? Give me the function. Now you have this yj as well. Yeah, just sum over yj. Worst case, you have an upper bound on how many shifts you have, right? Because you know that every task takes at most 8 hours. So even if you were to do one in each, you have this. Okay, cool. Objective function, done. So that's pretty much exactly what I've written. And then you want to do this minimization. Your next step is to identify constraints. And there's a few that you have that are readily apparent. right? Once a task is done, you can't do it again, right? So what do you have? So task is over i's, right? So before every task, yeah. So that's a little the complex one, nice. But there's an easier one, and that's just like making sure you don't repeat tasks and stuff. Yes.
So one shift or one task can only belong to one wait.
Yeah, a task can only belong to some one shift, exactly one shift.
For example, like a task belonging in two shifts can't happen.
Yeah, exactly. So xij would be one only for some j, for every individual I, right? So that's one of them. Does that guarantee that all the tasks are covered? It depends on the inequality. If we use equal to 1, it does. If we use less than equal to 1, then it doesn't, right? So we'll be using equal to 1, and that will guarantee that all the tasks also happen, right? So sure, I think that's the first one. Oh, no, the first one is the binary constraint. Great. Don't forget to write this down, actually. It's although the question mentions it, it's a good idea to just have it up top. It's a freebie. And then for every task I, you have the summation over all the xij, over all the j's, exactly 1, right? So each task can only happen in one shift, right? And there's this little text I've written up top. Your LP doesn't need to be standard form, as long as it's easy to convert, right? We've seen how to convert equality, so it's fine. You can just use equality and stuff. Okay. Cool.
Why are constraints in plain English?
Yeah, but I would prefer, because constraints, if you're passing it into your LP, you want linear inequalities, right?
So if we're waffling, write it in plain English.
Yeah, if you don't know how to convert it, then just write the English version. It's always a good idea to. So I think this is a step I've also already mentioned above. Describe the variables and their meaning, the objective function and the constraints. For each constraint, state what it means in plain form English. So you have to do that anyways. Guys, this paragraph is copy pasted onto your final. Read it now so you don't miss anything. I need justification on what these variables mean. I need justification for every linear constraint. Don't skip that. You're going to lose marks that you shouldn't have lost. Okay? Okay, and then like you said, you have to force for every shift the total duration of all the tasks within that shift. So the summation, for every j, the summation over all the i's should be less than equal to h, right? But there's a small little restriction, because we need to somehow enforce something. Well, right now, there's no relationship between the y's and the xij's, right? So I can have shift 1 here to be 0 and then x10, 1 to be true, and it doesn't really make sense, right? We want for every xij where you have some j, you want the corresponding yj to be true. So somehow you want to force that. And you can do that, yes?
If the sum of xij for a j, you sum over all the i's and xij, and if it's greater than 0, then yj is equal to 1.
How do you plan on doing if statements in a linear? But you're there. That's what you have to do. You have to find a nice way to compact it. And I propose that I take that inequality and I do something smart with it. For every shift, the sum of all the durations of all the tasks within that shift has to be less than equal to the duration of a shift times whether or not it was utilized. So if it wasn't utilized, then it has to be less than equal to 0. I can't use anything. And if it was utilized, it's h, right? So it's a 2-in-1 constraint that allows me to handle both situations, right? Now, if you do this, this is enough. I will give you one extra constraint, which isn't really necessary, but it will sort of streamline the output, the solution that you get. And that's this one. I don't want, let's say I can do it in 3 shifts. I don't want shift 4, 8, and 13 as my solution. I just want 1, 2, 3, right? So that's what I force here. Yes?
Sorry, in the previous constraint,
Yeah.
is that h times yj? Or
Yeah.
H? Okay.
Yeah, h times yj. So if yj is 0, that means the shift isn't utilized.
Yes.
What does that put as your upper limit? 0. I can't have any tasks assigned to that shift. And if yj is 1, that shift is utilized, only then I have an upper limit of h, right?
Oh, so it's not saying if it's used up, it's saying if it's like in use.
Yeah.
Okay.
Yeah. Yes? Well, this constraint just forces any solution to be of the form a bunch of 1s and then followed by 0s for the y's, right? 1a, 0b. All this means is, let's say the optimal solution only requires 4 shifts, and let's say I have 100 tasks. Then if I don't restrict it in this way, my solution, what the variable assignment will be for the y's, would be any random 4 shifts. Shift 13, 37, 84, and blah, 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 when it doesn't really make sense, right? You can just do 1, 2, 3, 4, and this will force that. But it's not necessary. OK. That's it, folks, for this review seminar. I have a bunch of extra practice questions for you, and I quickly want to go over the sample solutions. What sequencing constraint?
It says the task needs to be done in a sequence.
Right. Wait, did I miss that? Oh, whoops. So the solution will have it. The solution will have it. Don't worry. But that is important, the sequencing constraints. I am not implicitly forcing it anyways, so it is something that needs to be explicit. Sorry?
Can I ask you the question?
Question number 4? Yeah, sure.